Okay, and the last lecture I want to reserve. So next Tuesday there's no lecture. So last lecture I want to reserve for doing quotient spaces, and maybe revisit some of the theorems in linear algebra in the actually essentially one theorem in linear algebra which uses, it's sort of easier to follow using quotient spaces. Okay? Now that you've seen quotient groups, it would not be very difficult to appreciate why the definition of quotient spaces and why it's probably useful. So that would be so that's the plan for next Thursday, May 5th. And if I don't finish, I might take half an hour or 1 hour after 5th, but I will try to finish it quickly, 6th or 7th or something. Okay. Because 5th is the last lecture, I mean, last week of classes. If I don't finish whatever I intended to say about quotient spaces on 5th, I might take some extra time on a later date. Okay, so this week we will do a little bit more group theory. So I'll start with dihedral groups. And then we will start discussing zero theorems today, and then maybe okay, and then depending on how much time we have, the next lecture we will try to see some non-trivial example, okay, of using zero theorems. We will not be able to finish the proof, so I will skip the proof except for the first theorem. But all of them, all proofs are sort of repeated applications of the notion of group acting on sets in some way or the other. It's not necessarily the same action, but come up with a clever set on which some useful action, and then conclude something about it. Okay, so that's how it's proved. Okay. So this is a group of, this is a finite subgroup of GL2R. So which means invertible linear transformations of the plane, the Cartesian plane, and so this is a greater than let n greater than or equal to 2 given integer. Rotation by 2 pi divided by n. Okay. So sigma to the n is 1. Order of sigma is 1. Now tau, so okay.
Sir, could you just scroll up a bit?
I have not written
part.
I have
okay,
not,
okay, sir.
I haven't. L inside R2, some line, a line, I mean, a fixed, a line in through the origin. Okay, so this is something fixed. Okay, and now about the line. So now, of course, we're talking about the smallest subgroup containing these two elements. Okay. So a priori, when we say such things, okay, so it means that it needs to have all things of the following form. So okay, so order of tau is 1, is 2. Okay. So then the subgroup generated by sigma has n distinct elements. Okay. Sigma's, I mean, identity sigma square up to sigma to the n minus 1. And the other one has 2 distinct elements, 1 and tau. Okay. So any group element, so any element, every element of Dn, okay, can be written as, okay, some sigma to the A1 tau to the B1, sigma to the A2 tau to the B2, and so on. Okay, some finite sigma to the AN tau to the BN. Okay, so finite. Okay, and we can assume, I mean, suppose it actually starts with a tau and not a sigma, then we can assume that A1 is greater than or equal to 0. And similarly, depending on whether it ends with a sigma or a tau, at the end, we can assume that Bn should, I mean, we can stipulate that Bn should be greater than or equal to 0. And everything else should be positive. Otherwise, no point writing. And B1 is greater than 0, AI is greater than 0 for I greater than 1, etc., etc. Okay, so whether it starts or ends with a sigma or a tau, we may be 0. Okay. So that is, so okay, such expressions is what makes the group. Okay. We don't need to write inverses because these are finite elements of finite order. So sigma inverse can be rewritten as sigma to the n minus 1. Okay, tau inverse is just tau itself. Yeah, sorry. We could even assume that. Yeah, sorry. We don't need to write. Okay, so B1 is B1 up to Bn minus 1 are all equal to 1. Because if you don't need to write it if it's greater than 2, if it is 0, and if it's greater than 2, we can always write tau square as identity and reduce it. Okay, and you can always assume. And A2 through AN lie between 1 and n. They're not 0. If it is 0, we don't need to write it. Okay, just combine the tau terms, and they don't. And if they're above n, we can. So we can always write like this. Okay, but this doesn't tell us what the. This doesn't tell us anything about the. It doesn't even tell us whether the group is finite. I mean, as such, I mean, if you write like this, the group may be infinite. So if you want to actually simplify, and really of these expressions are actually one, sigma. Sorry, where is my pen? Not to look for relations among so what sigma. Sigma is rotation by 2 pi divided by n. And tau is reflection about some line. So relations. Okay, so let us say this is the line. This is the origin. Now there are two operations. Okay, so I would like to look at what happens if we. Sorry, let me just make sure. I think, yeah, tau sigma tau. So what is tau sigma tau? So tau sigma tau. So we are okay. We're thinking of these as functions. So they act on the left. So we need to start working out what happens to the rightmost function. Okay. So tau sigma tau. So let's take a point here. Okay. So tau reflects by the about the axis. So this is tau of p. So maybe actually maybe useful if I just give a little bit more space. Okay. And let us take a point here. Let us take a point here. So this is P. Then tau of P is here. Okay. Let us say that we rotate it by some angle. So this angle here is, so we should probably be here, 2 pi divided by n. So this is sigma of tau of P. And now we reflect it back. It would be here. Sorry, it's not completely to scale. So this angle here would be 2 pi divided by n. Tau sigma tau of P. Okay. From this picture, what we concluded is that, therefore, tau sigma tau is sigma inverse, which of course is sigma to the n minus 1. Okay. So let me just go over the argument again. I am starting with some p here. I'm applying tau, so it's reflecting about the line L. Then I am applying sigma, which is counterclockwise rotation by 2 pi divided by n. Let us say this is what the angle looks like. Okay. And then we are doing a reflection. So that would just be, let's just go here. But that would just tantamount to doing minus 2 pi divided by n from P. Okay. That's because this whole picture is reflected about the line L. Okay. So that tells us that sigma tau sigma is sigma inverse. Okay. So whenever we see an expression like this, sigma to the a tau sigma, sorry, it says tau sigma tau is sigma inverse. Okay. So then, this is what we have. Okay. And so therefore, tau sigma to the a tau would be sigma inverse to the a. because we can rewrite this as tau sigma tau to the a. Remember, tau square is 1. Okay, so I should technically be writing. I'm not making a. I mean, I'm not making that distinction, and this is sigma minus a, which again can be rewritten as a positive exponent. Okay, so this is what we. Okay, so whenever we have such a long expression, using this relation that we have just discovered, we can rewrite this thing. Okay? So this is what dn. So this is the relation between dn in dn. Okay, so specifically, we can check. Okay, it's easier to do this if you fix an L nicely. Okay, specifically, okay, let's say that L is the x-axis in R. Okay, so what does this? So what does then? Okay, so then tau then is reflection about the x-axis. So it fixes the unit vector, the 1, 0 unit vector, and the 0, 1 unit vector goes to 0, minus 1. Okay. And then one can check. Sorry, let me write. One can then check that. Okay. If we, okay, so let me write C for cosine 2 pi divided by n, and S for sine 2 pi divided by n. So then rho, not rho, this is tau. Okay, sigma will then look like cosine sine and minus sine and cosine, and then one can check that minus 1, 0, 0 minus 1 times cosine sine minus sine cosine is cosine minus sine. So this is okay. So one can check this. Okay. So this is just saying tau sigma equals sigma inverse tau, which is the same thing as saying tau sigma tau is sigma inverse. Okay. So if you are considering these two elements of GLN, then they have this relation. Sigma tau, tau sigma tau is sigma inverse. Okay. So using this, we can rewrite all of that group, and then we have okay, so all of those expressions, and then we will hopefully have a finite group. Okay, so that is what we will now prove. Okay. Proposition dn. So first of all, it says that dn is a non-abelian group. Okay. Generated by two elements of order 2n. Okay. This is what we need. So we will prove this. So just this is a hello. Sorry, was there a question? Okay. Yeah. Let's prove the statement now. So it is non-abelian. It's easy to see because from here we see that sigma, tau sigma, tau inverse is sigma inverse. Okay. So tau sigma is not same thing as sigma tau. So non-abelian, so proof. Tau sigma is not sigma tau. In fact, it is sigma inverse tau. So dn is non-abelian. Okay. Now we have okay, yeah, elements. So we can just list them. Just list. Yeah, we don't need to write. So this is what I just said. Okay. Sigma tau is not equal to sorry, tau sigma is not equal to sigma tau. So it's not an abelian group. Okay. The elements of D2n, the ones, let us write down the ones that we already know. So these we know. So maybe let us write. Let us enumerate the elements of D2. Okay, so we know this much. We know. Okay, so all that we now need to argue is that whatever expression that we have, we can always write it as tau times some tau to the a times sigma to the b. So now note that using the relation what did we write? Tau sigma equals sigma inverse tau. Tau sigma equals sigma to the n minus 1 tau. Okay, so whenever if it starts with sigma, we can always rewrite it using okay, we may assume that every element of D2n is of the form, I mean, for any element there exists AB such that tau to the A sigma to the B with A between 0 and 1 because tau square is 1, and B between 0 and n minus 1 because order of sigma is n my n. Okay, so therefore this thing here, let me call this thing star is an equality. Okay, of course we need to check that these are distinct elements. Okay, so that I leave as an exercise. Check that these are distinct elements. Okay, so the easiest way to so okay, maybe I should maybe I'll sketch it, okay, because it's a good idea too. Okay, so of course anything in the first half is, they're all distinct. Anything in the second half is also distinct. The only issue is some sigma to some a equals tau sigma to b. Okay, so the only okay, so I'll just check that case. So suppose sigma to the a equals tau sigma to the b. Okay, so okay, then multiplying by suitable power of sigma, we can assume that therefore tau is, so there is, so multiply by sigma to the minus b, sigma to the a minus b is tau. So in other words, the reflection can be written as a rotation. So this is rotation by uh, by a minus b times 2 pi divided by n. This is reflection. Okay, and how do we know that these are not? I mean, they can't be equal. Okay, so here is a sort of a geometric reason which sometimes comes across in some variation later or not. Okay, so this one's determinant is 1. This one's determinant is -1. Okay, so orientation, rotation is what is called orientation preserving. It preserves the orientation between vectors. If there are two vectors, one coming after the other, after rotating also, it'll come in the same order, okay? As opposed to rotation switches orders. So this is a concept that you will see, about linear transformations and sort of about vectors in calculus, in multivariable calculus. Okay, so this is, this. Okay? So rotation and reflection behave differently with respect to this thing. Okay, it swaps the order in which vectors come. If you take two vectors and apply a rotation, they'll remain the same order. Same order either you say the order is given by the acute angle between them in counterclockwise direction or something like that. You can define, but it just rotates the whole thing, as opposed to reflection swaps the order in which they appear. So therefore, this is a contradiction. Okay? I mean, a reflection cannot be written as a rotation. That's so. Therefore, these are distinct elements. I mean, that's the only non-obvious thing that's the only thing that needs some check. Okay, other things are clear. The first half, no element in the first half can be equal to a different element in the first half. No element in the second half can be equal to a different element in the second half. Can there be a mix between the first half and second half? And that's what I just did. Okay, so it's a non-abelian group of order 2n. So an immediate corollary is that D3 is isomorphic to S3. So we had enumerated all groups of order 6. Okay? There is a cyclic, every abelian group is cyclic of order 6, and and non-abelian groups are just is just S3. This we had checked earlier, okay? And in fact, one can check that this relation holds there. So it'll help. Okay? So we would like some geometric picture for Dn. So suppose we take a point. Take a point. Let us say on this line. Take a point, and then we apply this reflection and rotation by these things. Okay. So then what would happen is that we would. Okay. Now suppose that the line sort of divides a regular n-gun symmetrically. Okay. So I'll do two examples. N equals 4. So technically n equals 3. I have drawn the picture again earlier. We had discussed how to think of S3 as the group of symmetries of an equilateral triangle. Okay. So now I am doing this for a square. Okay. Let me label the vertices 1, 2, 3, 4. Okay. And the line L that I'm considering is this one. So now, because of this thing, we can also interpret D2n, Dn as inside Sn. Okay. So, and it'll become, okay. So the 4 vertices we are going to write like this. Okay. So now sigma then in this case is 1, 2, 3, 4. So I can think of this as an element. Okay. So what actually happens in the rotation for as far as the square is concerned, is concerned is that 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 1. Okay, so now that is the reflection, the rotation element is thought of as an element of S4. Similarly, tau. Okay, so now tau is reflection about the line. Okay, so it just swaps 1 and 2 and also swaps 3 and 4. And again, okay, tau is now inside S. So we can think of these as some special kinds of permutations. For example, the permutation which the cycle 1, 3 is not there in this group. Okay. What is there? I mean, cycle 1, 2 is not there. If 1 is swapped with 2, simultaneously 4 should be swapped with 3. Only then it becomes a reflection. Okay. So that we should keep in mind. Okay. It is only some special kinds of reflections, some special kinds of permutations are there in this group. Okay. And then we can verify tau, sigma, tau. Okay. So what is this? So we're going to read this from the right. So maybe I'll just write 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay. So we're going to read this from the right. Say 1 goes to 2, 2 goes to 3, 3 goes to 4. Okay. 4 goes to 3, 3 goes to 4, and 4 goes to 3. 4 goes to 3. Yeah. 3 goes to 4, 4 goes to 1, 1 goes to 2. And that is it. And 2 must go to 1 now. 2 goes to 1, 1 goes to 2, 2 goes to 1. Yeah. So I'm just reading from the right and see where they go. And this is exactly, if you think about it, the sigma inverse. Okay. The rotation which takes 1 to 4, 4 to 3, 3 to 1, and 3 to 2, and 2 to 1. So this is, so if you consider these two elements inside S4, they satisfy the same relations as if you were thinking about this as elements of GL2. Okay. So therefore, the subgroup generated by these two, therefore, subgroup generated by these two things, 1, 2, 3, 4, and the product 1, 2, 3, 4 is isomorphic to D4. And so we can think of D4 as inside, okay? So that as inside S4. Okay? Similarly, so just n equals 5. So now we take a regular 5-gon pentagon. Sorry, this may not look very regular or pentagon. I mean, it may not look very regular, just pentagon. Okay? So let us take this to be the line. Let us say 1, 2, 3, 4, 5. Okay. Take sigma, of course, is the rotation. So it should go take 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 back to 1. Okay. And tau, so it's a reflection about this line. So it doesn't do anything to 1. It swaps 2 and 5, and then it swaps 3 and 4. Okay. And then verify that tau sigma tau is sigma inverse. Okay. And sigma inverse, remember, is 1. So it's rotation in the opposite direction. So 1 goes to 5, 5 goes to 4, 4 goes to 3, 3 goes to 2, and 2 goes back. So check this, just the same way we did the earlier calculation. Okay. So therefore, these two permutations generate a subgroup of S5 isomorphic to D5. Okay. So any Dn can be thought of as a subgroup of Sn. So in general, so I will not prove the statement, but the proof goes exactly like this. In general, any for all n greater than or equal to 2. Of course, we didn't discuss what D2 is. D2 is just cycle 1, 2. Dn is inside S. It's a subgroup of S. I mean, in general, we proved earlier that any group is a subgroup of some permutation group, which is really you take the permutation group on itself, on the group itself. Okay. So that would be S of 2n. Dn has 2n elements, and we would take the S of that cardinality. That's how we in general embed, but these dihedral groups will sit inside Sn. So these are the rotational and reflection symmetries of regular n-gons. Square and pentagon is what we just checked. So this is so these things come up in various other questions about symmetries, which we are not going to discuss. Okay. I mean, there's a lot of symmetries about in the plane and in three-dimensional space. That one can devote maybe 1 month or 1.5 months on that topic, but we are not going to discuss that. But just the brief, and there these dihedral groups come up again, and various other things also. Okay. So okay. So now, so that's the discussion about dihedral groups. So now we want to discuss Silo theorems. So these are sort of important theorems about the structure of subgroups inside finite groups. Okay. So let G be a finite group. Okay. And P a prime number dividing the order of the group. Okay. So then we already saw Cauchy's theorem, which says that P, I mean, there is a subgroup of order P, or equivalently, there's an element of order P. So we saw already that there exists a subgroup of order P, equivalently an element of order. So we want to strengthen this result, I mean, substantially, and that is called three theorem. I mean, they call the first theorem of Silo, second theorem of Silo, and third theorem of Silo. Okay. So we will probably most of the applications require us to use all the three theorems. Okay. And so typically this will be used to say something about conjugacy classes about of groups of certain order. Okay. And they will typically. Okay, so typically we need a knowledge of all three theorems to apply it anywhere. But unfortunately, since we need to do this in 2 days, we will not be able to prove it in this course. Okay. So I will only prove the first theorem, and second theorem and third theorem I will state in the next class. Today I will not even state them because it's even to parse them, it takes a while, and then we will see 1 or 2 applications. Okay. But whatever I do in the next class, which is just statement and applications of Silo's theorems, will only be used in weekly in some. Okay, will not be used in the exam. Okay, because the statements are themselves very long, okay, and I won't. I mean, if I need to use it, I will state the theorems. I mean, I will write them in the exam, in the question paper. Okay? I will not expect you to remember the statements, but I may expect you to apply them, in some ways that we did in class, which we will do in class next. Okay? But definitely, I mean, the statement of first theorem is very easy. The second and third theorems that requires a little bit of writing, and I will, since we will have only limited familiarity with them, in this course, I definitely won't expect you to remember it for the final exam. So if I think about a problem that require them, I will give the statements. Okay. So now we want to state first Silo's first theorem. First first Silo theorem. Yeah, so the setup is as so let P be a prime number dividing the order of the group. Okay. So write the order of the group as write the order of the group as P to the E times M, where P and M are mutually coprime. The GCD of them is 1. I mean, P doesn't divide M. That is, P doesn't divide M. Then G has a subgroup of order P. Okay. So in other words, so okay, let us think about some. So we know. So in S3, this isn't saying anything new. Okay. So let us some discussion before we get into the proof. Okay. In S3, this isn't saying so. This isn't saying anything new. I mean, anything new meaning that we did not know already, since order of S3 is 6, and it is just 2 times 3. Okay. So, and we already know that we've already seen a proof of Cauchy's theorem. So we know that there is a subgroup of order 3 and subgroup of order. I mean, sorry, this has nothing to do with S3. In any group of order 6, this isn't saying anything new. Okay. Well, in order 8 also, this isn't saying anything new, because it is 8 is 2 cube, and it is saying there is a subgroup of order P 8. Okay. The P to the E is 8 itself. Okay. So this isn't saying. Similarly for 9. For 10 also, it isn't saying anything new, because 10 is 2 times 5. So if order of G is 10, again, it doesn't say anything new, because if order of is just 2 times 5, and we already know that there is a subgroup of order 2 and a subgroup of order 5. So the first case anything new comes is in if order of G is 12. Okay. So if order of G is 12, okay, then this first Silo theorem gives us a subgroup of order 4. Okay. How many such groups are there, etc., are dealt with in the second and third theorems of Silo, okay, which, as I said, we will discuss them in the next lecture and see how much we can learn about using them, but not the proofs. Okay. Proofs are, I mean, you have to set up some set, I mean, and then some action on it, and then count. Almost all of this is some application of the orbit stabilizer theorem and the sum of the orbit. So some variation of the class equation is what we will be using all the time. Okay. Not exactly the class equation. It may not be conjugation action, but orbit stabilizer lemma plus the fact that the sum of the orbit sizes is equal to the orbit of the group is what is most of the time used in proof of all these things, but different sets of actions and different, okay, there are different ways of using it. Okay. So it is, so this is, so this, okay, we would not have known this from earlier things, because we have not enumerated what all the groups of order 12 are. Okay. So at least we know some of them. We know that there is a cyclic group of order 12. We can take Z mod 3Z cross Z mod 4. We can take Z mod 3Z cross Z mod 4, 2 cross Z mod 2. So those things we can do. But okay, so now we know that there is a, if you take the dihedral group D6 that has 12 elements. Okay. We know another group which is the even permutations in four letters. I mean, S4 has 24 cardinality 24, even permutations has left cardinality 12. So we know some of them, but we do not know if all of them. So, but this is a general statement. Doesn't matter. We can, of course, enumerate. We can try to figure out what all the groups of order 12 and check whether the statement is true. But now Silo theorem just says it is true. Okay? This is, for example, as far as we are concerned, this is some new piece of information that is given by this theorem. And similarly, we can so for example, there is a subgroup of order 8 in S4. I mean, it is D4, but it's okay. But yeah, but that sort of things one can learn from this theorem. Okay, so as such, as I said, as such, this theorem may not. To see the concrete applications and in trying to determine what all groups are there of certain size, one needs information, not just the first theorem, but the second and third theorems also. And from using the three theorems together, one can actually make quite a good progress. So, but anyway, that's all beyond this course, so we will not worry about it. Okay. So, so we're going to prove this theorem, and I will follow the proof in Artin's book. Okay. There's a slightly different book, again using group actions. There's a slightly different proof in Lang's algebra book. Okay. I mean, it's a slightly advanced book, but it's highly, well regarded, and lots of people. I mean, at least for graduate courses, that's typically one that people. That's one of the typical thing. Okay. So I'm just going to follow the proof in Artin. Okay. Just remember. Sorry, just repeat. Yeah. So we are going to study some group action in order to prove this. And so the group that we're going to look at is, the set that we're going to look at, group is G itself. Okay. The set that we're going to look at is the set of all subsets of G of this cardinality P to the E. And then G will just act on the set of subsets. Okay. So this is something slightly new. This action is not something that we have looked at. Okay, so let us. So we're going to. So before we get into the proof, I want to describe the action of. Okay? But okay, so let X be the set of subsets of G of cardinality P to the E. Okay? So what we want to prove is that among these subsets there is a group. That's what we want to prove. Okay? But we will prove it in a slightly roundabout fashion, not just that directly. So this is what. Okay, so now I want to describe the action on this set. So action is just multiplication by G, elements of G on the left. Okay. G acts on X as follows. Okay. Phi G of some subset U is G times U, which by definition is GH, where H is inside. So it may look like a coset, but it is not. U is not a group. Okay? U is not a subgroup. Okay, so I should just want here. U is not a subgroup. Not necessarily a subgroup of G. So GU is not a coset. So just keep that in mind. We don't need to keep. We don't need to keep that in mind. But don't be confused about this point. That's all. Okay. So now, so this is what this thing that we would like to. So G acts on this set. Okay. So now we would like to apply the orbit stabilizer theorem for this one. So again, so this multiplication is what we would like to do. Okay. So just I hope this is clear. We're just multiplying. We're just taking. We're sending the set U to the set G times U, which is by definition this set. This is so G acts on this set. So therefore, so maybe I'll start the proof. Maybe I'll start calling this the proof itself. I was going to proof of first zero theorem. I was going to explain this action, but I think it can be explained in the proof itself. Okay. So G acts on X. So I hope this is clear. That okay. So now we would like to apply the orbit stabilizer theorem as well as the theorem. I mean the observation that the orbits cardinalities add up to the order of the group. Cardinalities add up to the order of the cardinality of the set. Okay. So now, so let us write O1, O2, etc. for the distinct orbits of this. So let O1, O2, OK be the distinct orbits of this action. Okay. So this is, so then we know that cardinality of X is the sum of the cardinalities of these things. So this we know. Now we would like to, so this is some generalities. We would now like to get some concrete information on what these numbers are likely to be, and from there conclude what we want. So I hope this is, so therefore, okay. So first we will prove a lemma, which is cardinality of X is not divisible by P. Lemma. Cardinality of X is not divisible by. Okay. What is the cardinality of X? Well, G has P to the E. P to the what did I write? P E to the M. So cardinality of X is the binomial coefficient order of G. Choose P to the E, which is just P to the E M choose P to the E. And so we want, okay, so this we can expand as P to the EM, and then P to the E minus E M minus 1, okay, all the way up to P to the E M minus P to the E plus 1 divided by P to the E minus 1 all the way up to 1. Okay. And then one can check that in each one of the pairs, there's no P, there's no more P. The first factor, there's no P. Second factor, neither of them is divisible by P. So the thing is not going to be divisible by P, okay, and so on. Okay. So this is, so then, so check. Okay. And okay. So this is the order of the order of this group. And so actually the details are in the book, are in 7.7. Sorry, just give me a minute. I need to open the book. 7.7. Okay. In Arden's book. Okay. So I mean, it is some. Okay. This is not some complicated calculation, okay. But okay, so this is what we would. So this is the the first lemma. So proof of lemma. Okay. So that says that there must be an orbit. I mean, there must be a summand on the right side, which is also not divisible by P. Okay. Therefore, without loss of generality, this is not divisible by P. Remember, the sum of the sizes of the orbit, they add up to the cardinality of X, which is not divisible by P. Therefore, there must be something on the right side, which is also not divisible by P, because if P divided everything on the right, it must divide left on the quantity on the left also. Okay. So this is, okay. So so write this as orbit. Okay. So let U be inside O1. So that is U is a subset of G, okay, of cardinality P to the E and its orbit, okay, has cardinality not divisible by P. Okay. So now comes the sort of the crucial part about what do stabilizers look like. Okay. Okay. So this is lemma 2, and this is 7.7.9 in the book. I mean, there it is written for slightly more generality, but let us just do this in the context that we need it. Okay. I mean, there is food for every, every subgroup, but we just forget about this. Okay. The stabilizer, the order of the stabilizer H of U, okay, for this above action, okay, divides this one, okay, and of course order of G. Order of G divides because it's a subgroup. Stabilizer is a subgroup. Okay? But it divides the order of U is what the new information is. Okay? So this is what we would now. Okay? So the second, okay, maybe I don't want to complicate this. That's how when we applied, we will apply it with that also. But this is the crucial new part. Okay. So, but what does this? So here, H is the stabilizer of this U. Okay. So then, what does what does it do to? Okay. So proof of lemma 2. Okay. Okay. So H is a stabilizer. So phi H of U is U for all H in H. Okay. That is what stabilizer says. Okay. But what does this mean? This means, so let us look at what does phi H mean. Phi H means, okay, maybe I should have, okay. Okay, so it should, the place of G is taken by H, and this H, let's call it little U. Okay. So this is just HU, U inside U is U itself. That's what it is. I mean, for all H in H. Okay. In other words, H is a permutation of U. In other words, H acts on U. So therefore, the action of G on X, okay, gives an action of H on U. Okay. I mean, now, so the sets are, I mean, U is an element of X. Okay. I mean, I'm not saying H is, there is an action on a subset of X. Okay. There's an action of H on a subset of G. Okay. So please make sure that this is what. Okay. So this gives an action of H on U. In other words, so that is phi H of U. U is just H times U. The point is that this is inside U. Okay, that is the where the that little h is, I mean, capital H is the stabilizer is used. Okay. So now the orbit stabilizer theorem says that now we are looking at an action of H on U and fix. So now this is just another application of. Okay. Yeah. So what are the? Okay. So now what are the orbits of this action? So the orbits of this action. So this is like H acting on H acting on G, but H actually fixes the subset U. Okay. This action are the right cosets of H. Okay. Given an element, U, remember, is also an element of G, and we're just taking this thing, the right. Okay. The orbits are exactly the right cosets of H and G. So, I mean, you have to think through this. I mean, write this down and think through this a little bit. Okay. Given a little U in capital U, if you just let phi H, if you apply phi H to it for all H, we would just be constructing the right coset capital H times U. Because this action of H on U is a sort of a restriction of the action of H on G, which we have looked earlier. Okay. So this is just. Okay. So therefore, all the orbits have the same cardinality, okay. And therefore, okay, and they add up to the. Okay. So all orbits have the same. Therefore, all the orbits have the same cardinality. Okay. Equal to order of H. Okay. Therefore, order of H divides the order of the set, which is the size of the set, which is. So this finishes the proof of lemma 2. Okay. So now, okay, so this, sorry, this is back to proof of theorem. This is the end of proof of lemma 1. Now we are back to the proof of theorem. Then we made another observation. So we needed a new lemma to understand that situation. That's the end of this, end of the proof of the lemma. Back to the proof of the theorem. Okay. So now we have established that the stabilizer's order has to divide the order of U and, of course, the order of G, because it is a subgroup. Okay. So therefore, so now let us take. So now U is in this orbit. Okay. So that orbit thing is not divisible by P, and yeah. Okay. So we have taken. Okay. Okay. So by lemma 2, order of H divides P to the E. Okay. This is order of E. Okay. So therefore, order of H is, I mean, H is a P group. Okay. So this is. Now, on the other hand, H is a stabilizer of. I mean, apply orbit stabilizer lemma to the action of G on X. On X, which is to say that H, this thing, this is the stabilizer of U. Okay. times this one, that is the orbit of U. This is equal to order of the group, okay, which is P to the E times M, and P doesn't divide M. So now let us look at what the options are. Order of H divides P to the E. Order of U1 is not divisible by P. Okay, so this divides P to the E. Okay. This is not divisible by P. And the product is P to the M. So the only option now is that is P to the E. And that is what we needed to prove. Okay. So it is a slightly I mean, there is stuff that needs to be built to proving this. Okay. I mean, just the mere knowledge of actions is not. I mean, you would actually set up a nice action and then sort of sit and analyze what happens at each stage. Okay. So I will just go over it once more quickly, and then next class I will state, and then we'll try to next two theorems, and then we will try to apply them to learn something about some finite group of small order. Okay, we won't be able to do it. Okay. Yeah, 12 I will work out, but and I think probably that's all that we'll have time for. Maybe 12 and 24 maybe. I'll see how much time we. Okay. Okay, so let me just quickly go over the proof again. So the idea is to study the action of G on subsets of cardinality P to the E. So P to the E is the largest power of P that divides the order of G. Okay. And the action is left multiplication. Phi G acting on the set U gives the set G times the set U, which is this one. Okay. Maybe it's a good idea to write U here itself. Just we don't. Okay, so this is an action. Okay, verify that. So now it has some distinct orbits called, let us say, K orbits, and call them O1 through OK. Okay. And then we have this equation that cardinality of the set is the sum of the orbit sizes. Okay. And okay, so the first lemma is that X is not divisible by P. Okay. So which is just the claim that this binomial coefficient is not divisible by P. Okay. And that can just sort of check, and the details are in that. So which means that the left side of this equation is not divisible by P. Therefore, there must be something on the right side that is not divisible by P. Okay. So let us say without loss of generality. So now we're back to the proof of the theorem. Without loss of generality, it is the first orbit whose order is not divisible by P, whose cardinality is not divisible by P. Okay. So take an element U. Now O1 is the orbit of U, okay, for this action. And let us look at the stabilizer. Okay. Call the stabilizer H. And the theorem, the next lemma is that that stabilizer has order that divides the order of U. Okay, so this is the sort of tricky part. So the point is that because H stabilizes U, okay, H stabilizes U for the action of G on the set X. H actually gives an action on U. So that's the key observation. Okay, and this action is sort of the restriction of the left multiplication action of H on G, which means the orbits of this action are the right cosets of H and G. Okay, so some right cosets will just fill out U. So the cardinality of U is a multiple of the cardinality of U is a multiple of the order of H. So that's what this lemma is. Okay. So this is the tricky part. Please make sure that you write out and make enough sketches and you sort of understand what's happening in this. So now we are back to the proof of the theorem. Now order of H divides P to the E. Okay. Now by the orbit stabilizer lemma to the initial thing that we started with, orbit of H times order of H times the size of the orbit is P to the E times M. So something that divides P to the E times something that is not divisible by P, not divisible by P, okay, is equal to P to the E times M. And there's only one conclusion from it, which is that the thing that divides P to the E must be P to the E. And this is a subgroup of order P to the E. Okay, so this is the first theorem, first zero theorem. Okay, we will now, the second theorem will say that all groups of, all subgroups of order P to the E like this are conjugates of each other. And the third theorem will say how many there are. Okay, how many there are up to some, it can't be precise, it's not a precise statement, but it gives good information. Okay, so I'll state those two things next time without proofs. Then we will try to apply them to some examples. So that's the plan for next lecture.